This is a review video for application of E&M. So before we do the application, I would like to just do a brief review on E&M as we did in the lecture. So here you can see I'm adding two more columns. So as we said, there are three players in E&M. One is a charge, current, and magnet. And we know the charge will create electric field, current will create a magnetic field, and magnet will also create a magnetic field. So it's kind of interesting that, remember, current is moving charge, but it acts more like a magnet rather than the charge. So if you want to find some more pictures, you can go to the lecture note 21. There I have like a picture for each of this case, and from there you can see more, you can kind of see things more clearly. All right. So now let's just generally talk about what's happening if I put a charge, current, magnet in a uniform electric field or uniform magnetic field, what would happen. When I put a charge in the uniform electric field, this charge will feel the electric field. Where electric field is a vector, so totally it will feel an electric force, which is QE. And if I put a current in the electric field, then nothing happens, because like current is just like a straight wire. It's the net charge on the current is 0. It does not react to electric field, and so does magnet, so nothing happens. And if I have a charge, put a charge right next to a magnet in the uniform magnetic field, this charge, if it's not moving, then nothing happens. But if it's moving, it will feel the magnetic force. A moving charge feels the magnetic force, where the magnitude of this magnetic force is just QVB. If there's an angle, you have a sine theta. If the angle is 90 degrees, then just QVB. And you will use right-hand rule 2. Right-hand rule 2 is for force. Right-hand rule 1 is for field. We will use right-hand rule 2 to determine the direction of force. So same for the current. If we put a current, we put some, like a wire of the current in the magnetic field, it feels a magnetic force. We will use the right-hand rule 2 to figure out the direction. So again, making sure that this would be your velocity or your current, this would be your field, this would be your force. If you are doing this, it will be more like, kind of up to you, like how you arrange it. But if you do this way, it's probably, this is velocity or current, and then palm will be your field, thumb will be your force. And of course, it's possible that you have different notation, but just making sure like we're all consistent. All right, magnet. If I put a magnet in a uniform field, so imagine I put a compass in Earth. If I put a compass on Earth, the compass will rotate. So when it's a rotation, we'll say it experiences a torque. The torque is, I put a compass, feel the field, the B field. So it has a torque. Again, this one you can use right-hand rule 2 to do that. So, okay, first vector, which is M, second vector, that's B, thumb is the torque, that resulting vector. All right. So now this is like really the core idea, like all the, this is all the equation that you learned about, relation between the field and the force. All right, so now let's come over and see if I put charge. So this is the same as this one, so let's we don't need to talk about this. When we have a charge and the charge, when we put a charge here, it creates a electric field, and this charge will feel that electric field happening at this point, so they will create electric force. So it has an electric force. And this is also the common where the KQQ over R squared coming from. Okay, so if it's only point to charge, it could be like point charge cases. You can have a lot of charges. It could also be parallel plates. But basically, for the charge, we can use Coulomb laws, and if the opposite sign they attract, the same sign, positive, positive, they will repel. That's the whole idea. All right, and what happens if we put charge next to a current? If we put a charge next to a current, all right, then what happened? So if I put a charge next to current, let's see, is there any electric field? No, because these two does not really react to each other. This will send out electric field line, but there's no, but this one has no net charge, so it does not react to this one. So nothing happens from the electric side. However, this will create a magnetic field, and the charge will feel the magnetic field created by this current. So what's happening here is current create a magnetic field. And then charge will react, will like feel this magnetic field if the charge is moving. So say if the current is going up, the magnetic field will be go counterclockwise. And then if I have a charge here, Q, moving in this direction, then I can use V, which is, I'm gonna draw the V in another way. So say the V is going in this way, and the current here, the magnetic field at this point, it would be out of page. This point, because it's like right at this part, it's tangential. It will go out of page. So we use V, B, up. So the force will be going up on this case. Okay, V, and this is B, and that's up. Force. Okay. So here, this guy also experienced a magnetic force. Okay. And so actually, I want to write it better. Let's see. It will experience a magnetic force, and of course we will use right-hand rule to determine the direction. But for the magnitude, you can see that this equals to the charge moving in magnetic field, and this magnetic field is the magnetic field created by the current, straight wire. Okay. Then of course the current is probably not straight. It could be a solenoid. It could be a loop. It could be many different cases in many different cases. But the whole idea is you need to find the induced magnetic field first and see how the charge reacted to that. So now let's see what happens to charge and magnet. If I have a magnet here, north and south, I have a charge here. Charge will send out electric field, but this does not react to it, so there's no electric interaction. But this will create magnetic field from north to south. And you can see this charge, if the charge is moving. If it's not moving, nothing happens. But if it is moving, we can see the field coming this way is somewhat pointing in this direction. Just right that moment is like somewhat pointing in this direction. So V and the B and the force force is going up. All right. So again, this is another case that they will experience magnetic force where the moving charge will feel the force, and this force is generated by the magnet, where this is generated by the current. Okay. All right. So that's 2, and a slightly more interesting case is current. This 2 current, they are just like 2 flow of charges, but again, there's no electric field. Interestingly, there's no electric field, but this will create a magnetic field at this point. So this straight wire will feel the magnetic field, which is into the page. So if I do I do field, force would be this way. And similarly, this will create a magnetic field. If we use right-hand rule 1, you can see this create a magnetic field in this direction, in this direction. So exactly at this point, because it's a loop, the direction keeps changing, but exactly at this point, that direction will be pointing out of the page, because it's like out of the page, like this, and then out of the page at this point. Okay. All right, so let's see. So now this current will feel the magnetic field and create a force. Let's see, current feel the field, which is this way, and then the force is to the right. So now you can see these 2 current traveling in the same direction, they will attract. If they are traveling in different direction, they will repel. Like this case, you can sort of use the same reasoning to find it out. And the force per unit length is mu naught I1 I2 over 2 pi r. Technically, you don't really need to memorize this equation. You can just kind of derive it by yourself. But it's just like an easy form to look at. So again, same direction, they will attract. Different direction, they will repel. All right. Then the next case that we can look at, current and magnet. Current and magnet. When we put a current in a magnet, the current will feel the magnetic force. Like we just talked about this case here, right? And the current doesn't need to be just a straight wire, it could be a loop. If it could be a loop, you will see this will feel a force. For example, if it's a loop current, let's see what happened. This one, current is going up, field is to the right, then the force will be going into the page, okay, into the page. And this one, current to the down, field to the right, the thumb is going up, so the force is going up. If I have a page like this, a loop like this, and this loop feel a force pulling up here, another force pulling down here. What's gonna happen is it will rotate. This rotate. Okay. So, and this torque, you can find this torque in the, later we will talk about the motor. You will find the torque for this motor. We kind of derive it in the lecture. So I'm not gonna repeat it here. I'll just quickly, it's like the whole idea is coming from this. When we have a magnet and a magnet, when a magnet and a magnet put together, they will rotate, right? It's just like this case. Okay, now rotate. All right, and so So this is just a chart for force, and like I will refer you to go back, and if you if you wanna like understand how magnetic field is created or electric field is created by charges, or how is it created by current, how is it created by magnet, I will refer you to the previous videos or your lecture notes. Okay, and now let's see how to use this chart to understand all different kind of application. So this is our just like selected application. Let's see the first one, speaker. So this is speaker. You can connect this to your phone, and your phone will send out the current. Like it could be, it's like up and down current. So say if the current goes this way, initially the current goes this way. Now you can see a current come this way, and then do the circle here. Okay. All right. So from the loop, you can see the current is going this way. Okay. So when the current going this way, the magnetic field generated inside in the center of this loop current or solenoid. It's not really a solenoid, it's just a loop current. It's like going downward. So which means you will see a lot of electric field line coming out in this case, like from this end. So this loop behaves somewhat like a magnet, where this is north, this is south, and the magnetic field line is going like this way. Okay, and here's a now if I put another magnet here, you can see this magnet and this electromagnet, there's a north and south, so they will somewhat attract or repel, depending on the direction of the current and the strength. So by this attraction or repulsion, okay, this vibration will further vibrate this wall, and this wall will vibrate the air molecule. This air molecule will vibrate your eardrum so that you hear the sound. Okay. So here we are using the idea of magnet and like a current and a magnet. We use a current to create an electromagnet, and that electromagnet will react to the current and the magnet. Okay, so this will react to it. All right, and so the next case I'm going to talk about is Hall effect. Say if I have a charge moving in the parallel plates, and this parallel plate has positive charge here, negative charge here, and it also has a magnetic field going into the page, like doing this area. So let's see what's happening here. What's happening here is this charge will, there are two fields here. One is B field, one is E field. And does charge react to electric field? Yes, charge will feel the electric field. So this charge will feel the electric field, assuming this is a positive test charge. So this charge will feel the electric field going downward. So that would be QE. That's electric force. And since this charge is also moving to the right, so it will also interact with the magnetic field, with the right-hand rule. V, B, so the force is going up. So this will feel a magnetic force, QVB. If you want to look up a table, you can see this charge. This is how charge behave in a uniform magnetic field. Okay, so now when if these two forces are balanced out, eventually this will just move to the right with a constant speed. Then you will have QVB equals to QE, and from there you can find out the speed is E over B. Okay, so by controlling E and B, you can control the speed of that ion. Another application is mass spectrometer. Mass spectrometer is saying, for example, if we shoot in two ions, these ions are singly charged, but they carry different weight. So say if I send in this one, and yeah, so like we have just like a pile of it, like a pile of like there's like a oxygen ion, and you can see a lot of them will oxygen 18 will what's the distance? Assuming, let's say this is D. If we just put oxygen 18, we will see this ion will travel this far, and then you will detect a lot of ion on the like at this point. So this point, the distance between this point and the starting point here, like the starting point here, you can see this is just the distance is D. And now if I put another ion which has less mass, and I want to know where I can catch it on this on the sensor, like what's the trajectory is gonna look like. So let's see. This physics is about charge moving in uniform magnetic field. Charge moving in uniform magnetic field. When charge moving in uniform magnetic field, it feels a magnetic force. And since right-hand rule, the V and the force is always perpendicular. So this force never affected the only change the direction of your velocity, but never the speed. And if it only change the direction, which means it provides centripetal force, so it's mv squared over r. Now if we connect these two, we can draw the connection with the with the mass and this radius. Okay, so these two ions, we can see that they share the same B. I can tune their speed so they're coming with the same speed. They are all singly charged, so the same Q. So you can see if it's heavier, it will travel further. So they both coming with the same speed, and they all travel in the same speed and fall down, like eventually on the screen, but they will share different radius. All right, so now let's see, since the mass is proportional to r, so if it's heavier, it will travel longer. So 18 over 16 equals to D over the distance for the oxygen 16. I'm gonna call it D prime. So by manipulating it, we will get D prime equals to 16D over 18. All right, so you can sort of use this kind of physics to design your experiment that you can, such that you can separate your ions, or find out the concentration of your a particular type of ions in a pool. So that's mass spectrometer, and now I'm gonna talk about what's a motor. All right, so now to talk about motor, let's see what's happening here. So I'm gonna draw another series of pictures down here from this view. Okay, so it's the same motor, but I'm just looking at it differently. So again, north is here and south is here. If I see it from the top, this one is not aligned with this electric field. Magnetic field. Okay, so this wire is this. This wire is at this end. Okay, so it's like from the top. And it's rotating, so after a while, you can see it will rotate to this direction. And then after a while, it will rotate to this direction. And then it will rotate to this direction. Okay. I'm sorry about the bad drawing. But let's see. So let's see kind of what happened. Right. And here I'm gonna draw another one, just to magnetic field. And this is my loop. This is I put this magnetic field here, and I put a current loop here. And this current loop, you can see it's connected to a battery, so this will send out the current coming in this way. So if I draw it, it will be like this. The current is flowing in this direction. All right. So that's this is my motor. Now let's take a look. When this one is aligned with, so in this case, you can see, if we see it from the top, this end would be out of page. This end would be into the page. Okay, if we see it from the top, right? Out of page and into the page. Right. So let's see what's happening here. First, on this end, the current is going up. Field is going to the right, so the force is going into the page. Yeah, it's into the page, and here current is down, field is to the right, so the force is out of page. If this end is into the page, this end is out of page, then this loop current will be pushed in this way. So this is the torque. So at this moment, it will feel a torque. Pushing in this direction and this direction. It will be pushed. Right? It will be like pushed, pushed, pushed. Okay? It will be pushed in this direction. And now when this one is just slightly tilted, because it was pushed over, so it started rotating. So when it's rotated to this direction, you see it from the top, it will look like this. Right? It looks like this. So now you can see the end, this end is the end that the currents, flow outward. This is the current flow, into the page. Now again, we can use right-hand rule. Like at this point, you can see current. At this point, this line, you can see current is going out. Field this way, so force is going up. Force is going up. Similarly, you can do the same thing here. Force is going down. So again, when this one is rotating, this one is rotating to this direction, it still feels a torque, but this torque is less than this one because of the angle. Okay, and now when it's completely straight, when it rotated completely, like perpendicular to this magnetic field, then let's see what's happening. Okay, so this current is going, the current going up. This point is now rotating to this way, and the current going down, if you see it from the top, it's now rotating to this direction. And if we use the right-hand rule, current going up, field to the right, forces to the up. And now this point is a current going down, field to the right, so force is going down. Now this paper, when it's rotating to this way, it will experience the force pulling in both directions, right? Pulling like both directions. this and that. So it just kind of balance out. So now you can see here we have this motor experience a torque to go in this direction, so it's here but slightly weaker, and this one there's like no torque at all. And how about this one? When it rotates over, the current going up is now rotated to this way. Okay, this out of page current is rotated to this way into the page current coming to this way. If we do the right hand rule, this is up, this is to the right. This is up field to the right, and the force is to the up. And this is like a current downward, field to the right, force is downward. Okay. So now once I rotate it over to this point, this force will pull this guy upward, this way, and this will pull in the other way. So you can see this guy will start to rotate in this way. So this one is experience a torque in this way. So you can kind of see this motor is gonna, rotate to the right, then no torque, then rotate back. Okay, so the motor will just like do this. So usually people will put some commutators or something here to adjust the current to make sure that it only go in one direction, so we can build a more useful motor. So in this case, you can see the torque is the maximum here, and the torque is the minimum here. The minimum torque is 0, meaning no torque, and the maximum torque is this way, and which is tau. So again, like you have the arm. Remember we do the seesaw problem, we have the arm, we have the force, and the force is magnetic force. So you take the arm times the force, then after some complicated math, you'll have N, I, A, B for your maximum torque. So where N is the number of the coil, I is the current running on it, area is just its area, and B is its magnetic field. Right, so that's it for the motor. And so the really core idea that I want you, so you can see the concept is not that complicated, but you just need to have a clear understanding is who is doing what in what field. Okay. The last example is this one. Remember we have talked about this one. These two, if they're the same current running in the same direction, so this one will feel a force. This current F2 will feel a force caused by this current. So it will feel a current 2 feel a magnetic field created by current 1, which is mu naught I1 over 2 pi r, because this one will create the field at this point like this. So from here we can calculate its force, the force per unit length. It's mu naught I1 I2 over 2 pi r. And the direction is gonna be, let's do this. The direction is gonna be to the left. And then similarly, we can do this for F1. So it will be the current I1 feel the force coming from this current. And then again, put in the equations, you will have the same force but in different direction. All right. So this is an important message. These two currents together pointing in the same direction, they will feel the same force. So it's if there's in the same direction, they will feel the same attractive force because of action and reaction force. So they must be the same. And the most important is if it's same direction, they attract. But if it's the opposite direction, you can do the same analysis, and you'll find that they will repel. So this is an interesting point: attract and repel, but with the same equation. So now if we look at more like a complicated example like this, say they all carry current I on this triangle where this is 60 degree, this is 60 degree, 60 degree. Then what's the force on each current? So I'm gonna call this current A, I'm gonna call this B, I'm gonna call this B. C. So the force on A, let's take a look. The force on A, these two are the current is both flowing downward into the page. So these two, they will feel the attractive force. So this will be attracted to this. And this similarly, so this will be attracted to this. If I draw the free body diagram, like draw all the forces on the A, it will be this direction. And where this angle is 60, this angle is 60, so half of it will be 30, 30. So I'm gonna call this FAC, I'm gonna call this FBC. So FAC equals to, per unit length, equals to mu 0 this current times this current, because that's their interaction in between, over the distance between 2 pi r. So I have mu naught I squared over 2 pi r. Okay. And these two, you can see the same current and distance. So FBC per unit length is also the same. So now let's see, if we want to add up these two forces, we want to do x component and the y component. And x component, we have FAC over L, like this force, times sine 30 minus FBC over L times sine 30. Okay, so you can see these two are exactly the same, so they cancel out. Now there's only y direction. Y direction from this y component is FAC over L times cosine 30 by pointing downward. Similarly, same here. Okay, so totally it's gonna be negative square root of 3 times mu naught I squared over 2 pi r. Yeah, okay. So this two, what's the force on the current at A? It is this force, where the x component is 0, y component is this. So if I want to draw it out, this will be my resultant force on A. So you can kind of do the same thing for B and C, and kind of following the same process. Now let's see, similarly to this question, but instead of the forces on each current, I want to just ask what's magnetic field at this point. So let's see, this point, since there's a current here, another current here, this current will create a magnetic field all over the place. This also creates a magnetic field all over the place. And specifically, this one will create a magnetic field like a circle. And since it's going upward, so the magnetic field is gonna go this direction. So exactly the P, the magnetic field caused by this, is moving to this way. Okay, and you can see it's a tangential line. So this is like it's the tangential to the to this circle. So it's a 90 degree. And now this one, so I'm gonna call this A current, call this B current. This P current also create another magnetic field that is a circle. If I draw it out, it will become like this. And where the direction of that field, let's use right hand rule 1, which is going downward, and do this direction. So the magnetic field on this is going clockwise. So exactly at this point, it will be going clockwise, so it will be going this way. So again, it's a tangential line, so this is 90 degree. If I want to draw a better picture here, so the first field created by A current, let's call it BA. It's this direction. And the field caused by this one, I'm gonna call it BB, B sub B. And the magnitude of the magnetic field at this point caused by A is mu naught IA over 2 pi r. And the magnitude, so this is called magnitude, this is called component. Okay, magnitude of that x component of the force, mu naught IB over 2 pi r. Okay, so you can see this is 60 degree, this is 90, this is 90. If you use 300, minus 90 minus 60, then you will have 30 left. Not really. How much would you have? Let's see, 120. You have 120 over this. Okay, so if you don't follow, I'm gonna slow down a little bit. This is 30, so totally there are 2 of them, so that's 60. And since it's a tangential line, so this is perpendicular to this. Okay, this is what we want. Okay, this is the same thing. Tangential line, that's 90 degree. And this is also tangential line, it's also 90 degree. So this part would be, 360 minus 90 minus 90, and then subtract it from 6 and 60. Totally here you have 120. If I split in 2, I have 60 and 60 on each side. So the total magnetic field for this point is 2-dimensional problem, so we need to separate into x component and y component. In x component, we have BA cosine 60 plus BB cosine 60. So which is 2 times mu naught I. IA and IB are the same current over 2 pi r because they share the same radius. Cosine 60 would be 1/2. Okay, so that's it. In the y component, we have BA sine 60 minus BB sine 60. So they will cancel out if you put in these 2 magnitude in. Okay. So this is your answer. This is the magnetic field at that point. Okay. So from this component, you can see that resulting total net magnetic field is pointing this direction, in the positive x direction. Okay, so that's all about the application of E and M. And again, so I want to stress on again that the whole point in this application is you need to have a deep understanding about what is doing what in which field. Okay, like who's the player and how they behave in this court. And once you realize that, when you see a problem that's probably a problem that you have never seen, but it's okay because you just need to figure out, hey, who's playing what, and in what court. And if it's in, sometimes it's not that trivial. It's definitely in electric field, or it's in magnetic field. But if you know there's some charge, other charges in present, or other current, a magnet, then you know this guy will generate electric field, this two will generate magnetic field, and then sort of use that to think about what's gonna happen.